So the neural network, when we have the neural network, we need to define the network topology. What is the meaning by network topology? So the network topology means we want to have the neural network, and it depends on the purpose. We can use the neural network for classification, and the classification can be binary. Binary, it means it is yes or no, or only two, 0, 1. Or multi-class. Multi-class means it can be more than 2 classes. Or we can use the prediction. So the prediction means the target is numerical value. We need to decide the network topology. It means we can specify the number of units in the input layers. So you can define how many units. Let's say this one we have 1, 2, 3. So we have 3 units in this input layer. The 3 units can be referred to 3 variables or 3 attributes that you want to use for this network. You can also define the number of hidden layers. Most probably, the number of hidden layers is 1. There is 1 hidden layer, but you can also have more than 1. If the hidden layer more than 1, then you need to specify. And also you need to check the number of each unit in each hidden layer. So when you have the hidden layer, maybe you think that the units are the same. So we have 1, 2, 3, 4. The other hidden layer we have 1, 2, 3, 4. But sometimes the number of units in different layer, it can be different. And also the number of units in the output layer. So if it is binary, usually we have 1. If we have multi-class, we can have many input units. It depends how many targets do we have. Normalize the input values for each attribute measure in the training tuples to 0 until 1. So the input value, for example, I have age. What is age? It is usually an integer number. It will be a number between maybe 0 until 100. Maybe. And you will have another variable, for example, height. The height of the general people, the ordinary people, maybe we can say between 90 until 200. So it is different. The range is different. So we need to make it in the same range for this neural network by doing the normalization. And we already learned the minimum maximum normalization. And we can have the input per domain value. 1 input unit per domain value. Okay, 1 input unit per domain value. The initial value will be 0. The output, if it is for classification and if it has more than 2 classes, 1 output unit per class is used. So, for example, do you still remember iris dataset? In the iris dataset, how many classes do we have? The iris data set we have 3. Okay. 3, what is that? We have the iris setosa, we have iris versicolor, we have iris virginica. So there are 3 classes. In that case, we can make 3 different units. But yeah, it depends. You can make also 2, only 2. Yeah. Let's say if it is 0, 0, 1, and this one is 0, 1, 0. Yeah, you can make also another which is 1, 0, 0. It means if it is setosa, then it will be in this unit. If it is versicolor, then it will be in this unit. If it is the virginica, it will be in this unit. Once a network has been trained and its accuracy is unacceptable. So the meaning of unacceptable means the accuracy is low. We want to get the accuracy which is high. Then we can repeat the training process with a different network topology. For example, I can add more hidden layers. If I have only one, the training accuracy is low. So I can have 2 hidden layers. If the hidden layers 2, the training accuracy is still low, then I can increase again to 3 hidden layers and so on. Or maybe we can have a different set of initial weights. So that might be helpful to increase the accuracy. So we come to a new algorithm, we call it backpropagation. Backpropagation is a neural network learning algorithm. Learning means training. Backpropagation learns by iteratively processing a data set of training tuples and comparing the network prediction for each tuple with the actual known target value. Maybe it's too long, but in short, usually you know why. The variable y, it indicates the actual value. And the variable y hat, usually it indicates the predicted value. So whenever we do the prediction or the classification, we always compare whether the prediction value is the same with the actual value or not. So this one, the backpropagation is try to compare, and of course at the end we will modify the weight. So the weight are modified to minimize the mean square error. So the goal is to get the minimum mean square error between the network prediction and the actual target value. The modifications are made in backward direction. If you still remember, we have the feed forward. The feed forward means we just go forward from the input layer to the output. But the backward means it is from the output layer through its hidden layer down to first hidden layer. So we call this is the backpropagation. So the training procedure will be like something like this one. We will do the initialization of the weight, and then the weight usually it is random. You may know from the previous example that we have. Okay, you still remember this one? how can we get the first weight? The first weight will be initialized random. And once we have the random values, we will propagate the inputs forward. Propagate means, as you know, we have the input and then we will go until the output. So if we call it this is feed forward, then we have from the input, we go forward until the output, and then we can calculate the cost. If we call back propagation, means it will return back to the previous and check the error. If the error is still high, then it will update the weight and then check with the latest cost. So we call the back propagation. Okay. We call the back propagation means we will propagate the errors and update the weight and the bias. Step 1 to 3 are repeated until terminating condition is satisfied. For example, when the error is very small, or when the percentage of tuple misclassified in the previous epoch is below some threshold, or when there is a specified number of epochs has expired. So there are many ways to stop this kind of network. So the parameters that we will learn, there are some parameters, for example, the bed size. What is bed size? So I give the Korean words here. Hopefully it will be helpful for you. So the bed size means the number of training example utilized in one iteration. For example, I define 100. So let's say I have a lot of data and I define 100. It means in one time, I will take 100 data, or in one time, I will take 100 frames. Okay. So let's say this is the video, and the video is separated into frames. And we have 100 frames of video processing. We call it, this is the bed size is 100. We have maximum iteration. It means the maximum number of iterations taken for a solver to converse. So let's say I have the bed size is 100 and I set the maximum iteration is 50,000. So it means it will run 50,000 times and for every 100 beds. So yeah, maybe the total will be something like 50,000 multiplied by 100, because every 100 we will like multiply until 50,000. Then there can be like 5 million times in total. Test iter. It means it indicates how many times the learning result are checked. So for example, we have the bed size is 100 and the test iter is 10,000. So we want to test for 10,000 iteration for every 100 bed size. Epoch, it indicates how many times you use the entire learning tuple to learn. So we have, let's say I have the 50,000 data and I'm using 40,000 for the training and I use the 10,000 for the testing. Then I have like 50,000 with the 100 bed size. So the total will be like 5 million. Okay. And then what we have now is the number of training set is 40,000. So I can check how many times that I will run for this training. So we will have like 125 epochs because we have 5 million divided by 40 million, which is the training data. There will be another part, we call it learning rate, but yeah, it is another parameter to control the training speed. If it is too large, it will overshoot. So the overshooting takes a long time. So it depends on the problems, and usually we use a very small learning rate. So this is an example. Let's say I have the total data is 2000. So I can define for every batch size is 200. So this 200 means I will select the 200 data, 200 data, 200 data, and then because I know that there are 2000 data, so it means there will be 10 iterations. After we finish with all those 200 for 10 iteration, we call this is like one epoch. And then we go to another stage, the same with the previous one, but the 200 data again, it will be selected randomly until 10 iteration, and we will get this is the second epoch, and so on until how many epochs that you determine. If you look at this one, I can notice this too. So if you look at this one means that the cost, it goes lower and lower and lower until a particular stage it is in the global optimum. So it depends on the learning rate. If you check this one, the learning rate is 0.005. It is very low. And the other is 0.05. It's a little bit higher. And you can look at when the learning rate is low, it shows that the decrement of the error. So this is the error. The decrement of the error is slowing down at some time and some moment that it will be in the global optimum. But if the learning rate is a little bit high, then it can jump, or because this is the overshooting before we reach the global optimum. That's why the learning rate determination is important. If the learning rate is very high, the number of epochs will be very high and the loss will increase. Actually, we want to minimize the loss. With the low learning rate, it will go down slowly until in some epochs, it goes to the lowest error that we want. Or if we have the high learning rate, it goes down immediately, but it may not go down in a particular epochs. Or we can have the good learning rate. The good learning rate is going down in a very good pace. So this kind of learning rate is difficult to mention here. Usually we just set a number 0.01 or 0.00001 and etc. This is the algorithm. I think it's better to see this other example. So in this example, we have the network x1, x2, x3. So it is the input. And we have the hidden layer. in unit 4, in unit 5. Okay, so there are 2 units. And we have P4, P5, it is the bias. We have output layer, we have only one. And this output means the prediction value, the probability of being class 1. So it is only the probability. If the probability is high, then I know that this will be class 1 in more certain numbers. Let's say the result is 0.9, then I can have certainty that this result is 1. So the remaining can be seen like this one. X1, let's put the initial input is 1, X2 is 0, and X3 is 1, and so on. So we have 2 values. Okay. Now let's try to put all the numbers into this network. So we have 1, 0, 1, 1, 0, 1 for X1, X2, X3. And then we put the weight 1 to 4. Okay. Weight 1 to 4 is 0.2. 1 to 5, it is minus 0.3. 2 to 4, it is 0.4. 2 to 5, it is 0.1. And so on. For the bias, we have theta. Theta 4 is 0.4 minus theta 5, it is 0.2, and theta 6, it is 0.1. Now, we know already the feed forward. When we learn the feed forward, we have variables x1, x2 until xi, and we usually use the weighted sum. The previous example, you use the weighted sum. How is the weighted sum? We have the x1 multiplied by the weight 1, like this one, plus the x2 multiplied by the weight 1, 2, plus, for example, xj multiplied by the weight 1j. Then we'll do the summation. So this is what we call as the weighted sum, plus the bias. It means we will do the plus with the bias, and we skip the activation function before. So the previous example, we just finished until this calculation. But today, let's try to figure out the activation function. This is the formula that I will use for the activation function. This activation function is the sigmoid or logistic activation function. The formula is like this one. So this is 1 divided by 1 plus E. E is a natural number, power of minus ij. So when you do the final exam, this kind of equation, you need to calculate by calculator. Okay? You cannot calculate by hand. So please make sure that in the final exam, you bring your own calculator. Okay. So I'm having this number 1, 0, 1, and I can just feed forward. Let's say I'm using the unit 1 to the input layer to this node. So I have 1 multiply 0.2, 1 multiply 0.2 plus 0 multiply 0.4 plus 1 multiply 0.5 minus. And then I'm going to plus with the bias, which is 0.4 negative. Then the result is 1. minus 0.7. And after I have the minus 0.7, as I mentioned here, we need to calculate with the activation function. What is the activation function here? It depends on the formula. Now I'm using the sigmoid function. Then I can just put the value 1 divided by 1 plus the natural number minus 0.7. How we can get minus 0.7? This is from this number. Okay. We have minus and minus, then it will be positive. So we have this formula 1 divided by 1 plus the natural number e power of 0.7. Then the value is 0.332. So we put this number to this unit. Okay. Next, I can do the same with the unit number 5. In the unit number 5, again, I can do the multiplication 1 multiply minus 0.3 plus 0 multiply 0.1, which is 0, plus 1 multiplied by 0.2. And then I will add with the bias 0.2. So the result will be 0.1. Now I need to put the activation function. The activation function is 1 divided by 1 plus the natural number power of minus 0.1. So 0.1 is from here. Okay. Then we can get a value which is 0.525. So 0.525, it is here. Okay. After we have the number 0.332 and we have the 0.525, we can use this number to calculate the last unit. For the last unit, we have the minus 0.3 multiplied by 0.332 plus minus 0.2 multiplied by, oh sorry, this is typo. Should be this one. This should be 0.525. Okay, I'm sorry, it's not 0.1, should be 0.525 and minus 0.1. Okay. Then this is the result. Okay. Hopefully the number is correct. And after I have this one, I will put it into the sigmoid function. 1 divided by 1 plus natural number minus 0.105. Minus and minus, then we know that it is positive. Then the result is, okay, somehow this number 0.474. So this is the output. And let's say this is the probability of being class 1. You know, the probability, if it is a higher number or it is higher than 0.5, then it is the high chance for this one is closer to class 1. Because this is still lower than 0.5, I can say that the probability of being class 1 is very low. Then we can assign this to the class 0. Now, after we have all those numbers, we need to calculate the error. So this error will be useful to later update the weight. How we can calculate the error? I'm using only this formula. So sometimes there will be another formula, but let's say using this basic network, I use this formula. So the error will be OJ. OJ means the actual output of unit J. 1 minus OJ, which is the actual output, and TJ minus OJ. What is TJ? TJ means the known target value of given training tuple. In the previous part, it mentioned that the probability of being class 1. So it means the target is 1. And in order to calculate the error, we have the output or the actual output, which is 0.474 multiplied by 1 minus 0.474 multiplied by Tj minus Oj, which is 1 minus 474. So the Tj, because we know that the known value for the given training tuple is 1, so we assign this 1, and it will be subtract with the 0.47. The value now, it comes with the 0.1311. So this is the error of this unit. After we have the error in the last unit, now we need to calculate also the error in the previous unit. So for this unit, unit 5, we can use this error formula. Why we need to update with this formula? Because this node may have two different arrows. For this example, we have only one. But let's say if we have two, then we need to sum all the arrows. Now we have only one, so the output of that respective node, which is 0.525, multiplied by 1 minus 0.525. Now we have only one. This is the unit 6. So we will just do the multiplication of the error k, which is 0.31311, multiplied by the minus 0.2, minus 0.2. So minus 0.2 is the weight from the J to the K. So by using this formula, we will get the numbers like the error is minus 0.0065. And we put this as the error in this unit. And we can do the same for the unit 4. In the unit 4, we have the 0.332 multiplied by 1 minus 0.332 multiplied by what we have from the unit 6. So the error is 0.1311 multiplied by minus 0.3. So the minus 0.3 is the weight. Then this is the value. So we put this value as the error rate in the unit 4. So what we need to calculate is only the error rate until the first hidden layer. So you don't need to calculate again the error in the input layer. So you just need to calculate the error until the first hidden layer. Now, after you have the error, we need to update the weights. How to update the weights? So I'll give you this formula. The delta Wij, it means the L, there's another parameter L, we call as the learning rate. Okay, so this learning rate is, you can determine, like what I mentioned before, the smaller learning rate will be better. For this calculation, so I'm just using a high number. I use the 0.9 just to show the examples. If the number is too low, I'm afraid that it will be difficult to calculate. So the delta Wij is a result of multiplication the learning rate multiplied by the error j multiplied by the y. So what is one? Let's see later. And this formula, we will update the new Wij. Wij. So if you learn programming, you will have like A equals to A plus B. What does it mean? The new value of variable A equals to the current value of variable A plus B. So what we want to do here is the same. The new value of Wij equals to the current value of Wij plus the delta Wij. So you can see if we want to update the W for 6, what is it? Minus 0.3. How we can get this one? This is from the previous weight, minus 0.3. So the current weight, which is minus 0.3, it will be updated plus by the 0.9, which is the learning rate, multiplied by 0.1311, which is the error from the latest node, and we will multiply with the output, which is 0.332. Then this will be the new weight, minus 0.261, and we will update it here. What about the W56? We have minus 0.2. How we can know the 0.2? It is from here. So the minus 0.2 will be updated by adding with the learning rate multiplied by the error in the unit 6 multiplied by the output in the particular unit. So in this case, in the unit 5. So the result is minus 0.138, and we put this here. Okay. Now, we also have another, let's say just, I can try only one more. Okay. W14. W14, the first node or the initial weight, it is 0.2. So you can check. The first is 0.2. Now, I would like to update the value by adding with the learning rate multiplied by minus 0.087. This is the error in this unit multiplied by 1. What is 1? 1 is the input value. Then we can get the result 0.192. So this value will be the updated weight from weight 1, 2, 4. We can also update the bias. How to update the bias? Sorry, I didn't put the formula, but you can look at this algorithm. So the bias can be increased with this algorithm. The delta bias is the learning rate multiplied by the error. So the new bias will be the current bias plus the delta bias. So you can look at this formula. By using the same formula, then I can update 0.1. 0.1 is the bias here, multiplied by 0.9, which is the learning rate, multiplied by 0.1311, which is the error. This is the error in the unit 6. And then the value 0.218 will be the new bias. We have 0.2. 0.2 is this bias multiplied by the learning rate 0.9 multiplied by the error in this unit. So the new value is 0.9194. We get to update this bias. And the last one, this is the bias here, 0.4. Then we multiply with the learning rate 0.9 multiplied by the error in the unit 4, which is 0.0087, and it will be updated here. So after we have this one, what will we do next? Again, we need to do it forward. So 1 multiplied by this, 0 multiplied by this, 1 multiplied by this, we get the value here. And then again, we multiply by this and this multiply this, we get this value. And we will check whether the error is minimized or not. If it is already minimized, then stop. If it is not minimized, then we again do the iteration until we get the minimum value. So this neural network has some weaknesses. It is long. It's long in the training time. And if you have more layer, of course, it will increase the training time. And it requires a number of parameters. So as you know, we need to determine the learning rate. We need to determine the bias, and we need to determine the epoch. We need to determine the maximum iteration. We need to determine the batch size. So there are so many parameters. And poor interpretability. It is difficult to interpret the symbolic meaning behind the learned weight and the hidden units. So what does it mean by the layer? We don't know. What does it mean by the weight? We don't know. So we just fit forward into the weight without any interpretation. But the strength is, it is high tolerance to noise data, the ability to classify untrained patterns. So if you cannot find some patterns in the training data, then it can detect, it can classify. Well suited for continuous value inputs and output. And in the successful of array and the real world data, which is the handwritten letters, so it is already successful. And the algorithms are inherently parallel, so it can work in the parallelity in the neural network. And the techniques have recently been updated or developed for the extraction of rules from the trained neural networks. So we can use like the pre-trained model, the existing neural network can be used to train a new problem. Okay, so that's all about the neural network. And on Thursday, I think I will give you also another learning check. So please try to review what you already learned today. Okay.